Good morning, AP Chemistry fans. I hear the church bells going off across the street, which must mean it's 9 o'clock here in the Chicagoland area, and it's time for another great AP Chemistry lesson. Hope you all are doing well and staying safe out there. Mr. Faribaugh and I have some great things to share with you today. Today is going to be real lab heavy. We've got 3 different lab techniques that we're going to get to talk about that I am really excited about and think that you're going to enjoy. So just a quick couple of reminders for what this is going to look like. Today's Tuesday, April 7th. I'm Mr. Byrne from Glenbard West High School. Go Hilltoppers. Thanks for joining us today. We're going to continue our discussion of Unit 3, which is generally on intermolecular forces and properties. But like I said, we're going to be looking at some solutions today and specifically some different labs that we can do in order to analyze solutions. For all your questions moving forward, just a quick reminder to go back to apcentral.collegeboard.org and check there for the most up-to-date information. If you haven't had a chance to look at yesterday's video yet, you know that you may not know that the dates for our tests were released on Friday. So the AP Chemistry exam will be on Thursday, May 14th. Remember that everybody will be taking the exam at the same time. So you would want to find the time zone that corresponds to where you live and go ahead and mark your calendars. So I'm in Chicago in Central Time, and so we'll be taking the test at 1 p.m. But if you're on the East Coast, you would be at 2 p.m. and so on. International students, the best way for you to probably calculate your time would be to look at Greenwich Mean Time and then calculate from there. If for some reason you have a conflict with that first date, you would want to talk to your teacher or whoever your AP coordinator is at your school about using one of these, the alternate dates. I'm sorry, not one of them. There's only one alternate date for AP Chemistry, and that would be on Tuesday, June 2nd. One piece of information that we did not specifically talk about yesterday was the format of the exam. And again, all of this is on apcentral.collegeboard.org. I just wanted to highlight 2 things for you quickly. There will be 2 questions that will be completely free response. So remember that there's no multiple choice questions on our exam this year. The 2 free response questions, one of them you will have 25 minutes to read and respond, and then 5 minutes to upload your response. And once you've uploaded it, you cannot go back. Then you'll look at question number 2, which is a little bit shorter, 15 minutes to read and respond, and then 5 minutes to upload. The format of the questions will give you some sort of chemical system, some data, and we're going to look at your ability to explain phenomena using models. I'm not going to read through each of these bullet points, but I hope that these bullet points look very familiar to you, because these are ones that Mr. Faribaugh and I are going to have been highlighting often in these lessons, and will continue to highlight. You notice that we have not given you any multiple choice questions to answer as we've gone through these, either for practice or for homework, and we try to keep coming back to these skills to make sure that you're really feeling confident on them for when exam time comes. Okay, so this is a great slide if you want to take a screenshot of it, or if you want to just, like I said, go back to apcentral.collegeboard.org. All of this information is going to be available there for this exam and for all of your exams. So like I said, today's lesson is going to be similar to our lessons, the format at least of our lessons from previous days. We'll start out with a review of yesterday's homework problems, and then we're going to look at 4 lessons that are really all around solutions. The theme that we're looking at here is around solutions. Friendly reminder that you may stop at any time that you need to re-listen to something that I'm saying if you want to try to work ahead and come to a solution to the problem before I give you my solution. Have some pencil and paper available. And there are just a couple of diagrams today from OpenStax, but that's a great resource for you if you are somebody who likes to read about these topics before you go into our explanations of them. It'd be a great time to stop right now, pull out your textbook, look up any of these vocabulary words here: solutions, mixtures, chromatography, solubility. Any of those things would appear in your chemistry book as well. You can read up on them and then look at some of our explanations about how they would be applicable on the AP test. So our warm-up was asked you to look at this problem from a practice exam where we're analyzing magnesium reacting with some hydrochloric acid to make magnesium ions and some hydrogen gas. So this is strongly connected to what we talked about yesterday because we're going to be producing gas. However, our 4 problems here are a really nice reminder of multiple parts of lessons we've talked about over the past couple of days and weeks. So we'll attack each of these problems independently and then go from there. Okay. So this first step, I hope, is a pretty straightforward one where we calculate the number of moles of magnesium in a sample. So we're going to start with a number that's given to us in the problem. We're going to use the molar mass off of the periodic table that was given to us. We use a nice dimensional analysis here where we have our moles on the top, grams on the bottom. We're going from grams to moles. And so our final answer is straightforward 0.00148 moles of magnesium. This is a great example of how a pretty complicated problem can have a simple start to it and maybe even build up your confidence as you're trying to attack a problem like this to just start working on it, and you'll slowly get to the point where you're feeling really good about your overall solution to the whole problem. The second part asks us to calculate the number of moles of hydrochloric acid that's needed to react completely with the sample of magnesium. So here we're going to start with those moles of magnesium that we had here. So this is essentially just a stoichiometry problem. If we know how many moles of magnesium we started out with, we're going to be able to tell how many moles of hydrochloric acid are needed to react completely with it. Okay, so we're going to use stoichiometry, perfect magic chemistry land. If we have this many moles, exactly how many moles of hydrochloric acid do we need there? We have 2 moles of protons for every 1 mole of magnesium. This is identifying that hydrochloric acid is a monoprotic acid. It has 1 proton on it. So we're going to need 2 moles of H pluses for every 1 mole of magnesium, our mole ratio from the balanced chemical equation. And that gives us 0.00269 moles of protons that are needed to react completely. Excuse me just for a second. Right, so hopefully those 2 steps were pretty straightforward. This next step is a lab that many of you may have already done in lab in class before you left for this extended break. Just in case some of you have not, I'm going to just go through one of the procedures for how you might have done something like this. There's a couple different ways that you could collect it. This method of gas collection by water displacement is a pretty common one. There are multiple different explanations of it online. So if you'd like to see another example of it, feel free to just do a quick Google search and find some other videos of this. But what I have here is a setup of this long, tall piece of equipment is called a eudiometer. And eudiometer is essentially either a large upside down test tube. It could be a large upside down graduated cylinder. It would have graduations on here. It would have markings that tell us what the volume of solution is. In a lot of ways, it looks a lot like a burette. Whereas a burette would be open on both sides of it. This is open just on the bottom. For this setup, what we've done is we've put a rubber stopper in it, but this rubber stopper has a small hole in it, and that hole is going to allow water to be displaced if we produce gas. And so or liquid to be produced. What I'm going to show you is that in this experiment, what we would do is we would put a piece of solid magnesium at the bottom of this container, and we'd put some sort of solution of aqueous hydrochloric acid. So here is our magnesium and acid from our equation. Okay, some setups you will put a little bit of hydrochloric acid in the bottom, fill it up with water, and then when you turn it upside down, the hydrochloric acid will fall down towards the bottom, and then it's when they meet, what you're going to see is that bubbles start to form. I saw one experiment where the teacher had put some food coloring in the hydrochloric acid. So the hydrochloric acid was green, the water was clear, and you could watch the green hydrochloric acid come down until it meets up with the solid magnesium. There's multiple different ways that you can do this, but what we do know is that as gas is produced, because it is less dense than the aqueous solution in there, we know that the bubbles are going to float to the top like so. And so if this was an experiment you were doing in your class, you would see the solid magnesium at the bottom. You would see it reacting and probably getting smaller with a lot of bubbles that are around it. And as those bubbles start to reach the top, what we're going to see is that it collects a certain volume of gas at the top. Now here's where that hole at the bottom of the stopper is important, because as we displace the water, as this gas is produced in here, some of the solution can come out into this beaker of water, and we would see this the level of the water rise in this because it was being displaced. So we would continue to watch this experiment while the magnesium is reacting until the magnesium is all used up. Okay, so what just happened there is at some point the magnesium is completely used up. Okay, and we know how many moles, right? We put a piece of magnesium that was 0.0360 grams in here. We know how many moles that was. There's still going to be some bubbles that will continue to go in, and they will be collected up at the top. Okay. Now, oftentimes what we will do is we use a giant beaker so that we can put the water level here equal to the water level here, and then we know that the pressure inside the container is equal to the room temp or the room pressure, right? This experiment was actually a little bit easier because it told us that what the pressure of the gas in this collecting tube was. They had some sort of a measuring device. They were able to measure it directly. So it's not necessary for this experiment. If you did this in your class, you may have worked to get this liquid in here, even with the liquid that's right here, so that the pressure inside there is the same as the pressure in the room. Okay, so the question that we have to ask ourselves as we're looking at this is what gas or gases is inside the eudiometer at that point? I want to give you a second just to consider that before we move on, because all of this is just set up for what is part of the problem that was explained to us. It's all set up to look at what this question is ultimately asking us about. And the key understanding for this kind of a lab is that we absolutely have hydrogen gas in that container in the eudiometer at that point, because we produced hydrogen gas over here, right? Here's our product, hydrogen gas. You'd have a solution in here that would include some magnesium ions. But because of the way this was collected by water displacement, we will also have some water vapor in there. And if we were to zoom in really closely on there, you would actually see some condensation on the side of the eudiometer. You would see that there are maybe some droplets of water in there. And then the assumption is that the water vapor is trapped in there as a gas. And that makes sense. It makes a lot more sense when we read the next step in the problem. If we connect this back to what happened with what we talked about yesterday with the laws of partial pressures, we know that the total pressure in there, which was 749 torr, is equal to the pressure of one gas, which is hydrogen, and plus the pressure of the other gas, which is water. 749 is equal to the sum of both of those. Right? So then we look at question C says, given that the equilibrium vapor pressure of water is 21 torr at 23 degrees. And I think if we go back maybe to Friday or Thursday of last week, Mr. Faribaugh talked about how this vapor pressure of water is dependent upon temperature. So this would change only at different temperatures. So our problem is telling us at 21 torr, we have 23 degrees Celsius. I'm sorry, it is 21 torr at 23 degrees Celsius. So we can just plug that in right here for our vapor pressure for water. And that tells us that our pressure for hydrogen is equal to 749 minus 21. And our final answer, right, calculate the pressure that hydrogen gas produced. So just the pressure of hydrogen, if it were dry, is 728 torr. Okay. So that's relatively straightforward if you understand this experiment, right? Like many things we've talked about over the past couple of weeks, the math here is not necessarily challenging math. It's understanding the chemistry that's involved in this setup that's going to help you to be able to get to the problem set up in the proper way. This the partial pressure equation per se is on our equation sheet, but you just would have to know that we have multiple gases in there to be able to solve for it. Then the last part of this is to go from all this information that we have here to calculate the volume. And here you'd want to understand that based on all this information we have, we've talked about moles, we've talked about pressure, we have some temperature information in here, we're trying to get to volume, that we must have to use the ideal gas law, PV equals nRT, or pressure times volume is equal to number of moles times our gas constant times the temperature. I'm going to just list out the information as it's given to us in the problem. We're going to use the partial pressure just for hydrogen because this question is asking us about the partial pressure or about the volume of just the hydrogen that's in there. So we would use the pressure of hydrogen. I'm sure that it was a common mistake for students to just go back to this. What we would want to make sure is that students are using the partial pressure just for hydrogen to solve this problem. We're looking for volume, our number of moles of hydrogen. So here again, we have similarity here, the pressure of hydrogen and the moles of hydrogen, which we had from earlier on, is these are the number of moles of hydrogen that's produced, right? So that would be the same number of moles. We just did the stoichiometric analysis here. How many moles of magnesium did we start with? That's how many moles of hydrogen. I can see a student also getting confused that they should use the protons of the H plus ions, but no, we need to know the moles of hydrogen here. So that's why this is 0.00148, not that doubled number. Our R stays the same here, okay? And our temperature as given to us in the problem is 23 degrees Celsius. So one of the things that I suggested yesterday is that we use our equation sheet to remind us what our units need to be. And while we have a gas constant down here that gives us where we could use torr, so if that's something that you're used to doing, you might want to use this gas constant, 62.36. In my class, we always go back to 0.08206 liter atmospheres over mole kelvins. That's just the way that I was taught to do it and what makes sense to me. So I'm always going to convert back to these, but there's multiple ways that you could solve this. It's nice that this equation right here, or the conversion between atmospheres, millimeters of mercury, and torr is right there. So the first thing we need to do is to convert my torr into ATMs. And then I also need to convert my degrees Celsius into Kelvin. Okay. Again, there are multiple ways that you could do this. If you felt more comfortable using this equation or using this gas constant, you certainly could do that. I'm going to rearrange my equation to say that volume is equal to nRT over P. I plug in my numbers, do a quick solution, and my final volume is 0.0375 liters. This is another example of where you want to make sure that you have included your units. And look, we go back to the problem, says we need to give a solution that is in liters, okay? And so giving it in milliliters would not be appropriate because this says in liters, and so we would leave it here. Of course, if this number seems weird to you and small, this is like 37.5 milliliters. So seems a pretty reasonable amount of gas for something like that. Whew, that was a really long problem. Okay, this is a good example of an extended kind of a problem and how College Board loves to give us problems that have multiple steps in it and to test our knowledge of multiple aspects of chemistry. And so I hope that you're feeling confident after looking through this, but feel free to stop and go back and listen to a couple of things that I said as we went through here. Okay, I'm gonna go through a couple of quick lessons on each of the topics coming up and some practice problems moving forward as well. We're going to talk about solutions and mixtures and how we could represent them, talk about two separation techniques, and then look at the solubility, how we would talk about solubility per se in solutions. Okay. So this first topic, 3.7 solutions and mixtures, we're really going to get into the math. This is a lot of making sure that we have some really clear ways of calculating out the molarity of a solution. Okay, and I assume at this point that most of you are pretty familiar with molarity, but we'll just do a quick review of it to make sure that we're all feeling confident. Two vocabulary words that are listed in this topic are homogeneous mixture. So when we think about a homogeneous mixture, we should think about the fact that their properties do not vary throughout the sample. So if I took a piece of this sample, or I took a piece of this sample, or wherever I take it, the makeup of this solution would be the same. Okay, so a solution is a homogeneous mixture. It can be a solid, a liquid, or a gas. We're going to spend a lot of time talking about liquid, but you know that air around us is a mixture of gases. There are certainly some solids that would, especially metals, that would be homogeneous mixtures. that we could look at as well. A heterogeneous mixture, to compare homogeneous with heterogeneous, we know that the macroscopic properties depend on the location of the mixture. That's just a fancy way to say that if I take a sample from one side versus the other side versus in the middle, the properties or the makeup of that solution is going to be different. So these two mixtures are actually made up of the same kind and number of particles, if I did that correctly. However, the way that they're distributed throughout the sample is different, and that's what makes this a homogeneous mixture versus this being a heterogeneous mixture. Okay. Solution composition, we can mathematically represent it in multiple different ways, but the most common thing that's used on the AP chemistry exam is molarity. And this is one of the foundational equations that we use time and time again. I think you've seen Mr. Fairbaugh and I refer to this several times already. And so make sure that you are feeling really confident in this moving forward, okay? So I put out 3 problems right here, and I want to encourage you to break yourselves into some groups. And today what we're going to do is we're going to consider what kind of pizza you like to eat. So if you're somebody like me who likes to eat pepperoni pizza, I'm going to encourage you to do problem number 1. Stop at just solve problem number 1 and then join us again. If you're somebody who likes to eat sausage pizza, then you can go ahead and do problem number 2. And if you're a classic cheese pizza or you're from New York and you call it plain pizza, you want to do problem number 3. Stop what you're doing right now, solve out your problem number 3, and then come back to us in a couple minutes once you have a solution to your assigned problem. I'm going to give you 5 seconds here to pause. Okay, and now we're back, and I'm going to look at each of the solutions that I came up with, how to solve these problems. They're all a little bit tricky in their own way, and what I want to point out is that it's going to be very rare that somebody's going to ask, or on an equation on the AP test, that we're going to be asked a direct what's the molarity of something just based on moles and liters. That might be a way for you to warm up and for a way to you to do some simple practice, but these problems are they're always going to be a little bit more complex as we try to solve them. So for problem number 1, we're going to remember that our equation is molarity is equal to moles of solute, right? So whatever is being dissolved in the liters of the overall solution. So it's not the liquid that's added, but it's the liters of solution. So you notice that this tells us that we have 1.65 liters of solution, right? It's not that we added 1.65 liters of water. We made sure that the final volume of the solution is 1.65 liters. So I'm going to start with moles of solute, 56 grams of SrI2 strontium iodide. The molar mass of that is right around 341. I think there's a couple decimal points if we use the periodic table. And then what we also want to recognize is that in this compound, that there are 2 moles of iodide ions for every 1 mole of strontium iodide. So that was the key of the trick here, that we're going to do a conversion from grams to moles. And then we have to double that to make sure that we're taking into account the fact that strontium iodide, when it dissolves, produces 2 ions of iodide. And so we should come to a solution, I'm sorry, with the number of moles of solute is 0.328. And then we can go back and we can plug that into our equation up at the top, moles of solute over liters of solution, and we get something like 0.199 molar. Okay, problem number 2, we're going to start out with our same equation, but we need to rearrange it because we're looking for our number of moles, right? So moles of sodium ions. Again, this is going to be a little bit tricky. I hope that our sausage pizza fans out there are people that are, you recognize that we have 3 moles of sodium for every sodium ions for every 1 mole of sodium phosphate. Okay, and so even though our overall solution had a concentration of 0.1 molar, our concentration of sodium ions was 0.3. Okay, and so when we plug that in, we're going to get our final answer would be our number of moles of sodium ions is 0.0735 when I multiply those numbers together. Then our cheese pizza fans out there had a pretty complex formula up here. We have what we call a hydrate. So this is not just copper sulfate, this is copper 2 sulfate, we call it pentahydrate. And so what that means is that when copper sulfate, this copper 2 sulfate is in its solid form, it actually absorbs water, and it absorbs water at a predictable rate. So for every one particle or one molecule of copper 2 sulfate, there would be 5 molecules of water that are incorporated into the crystal structure. And so that's going to affect the molar mass, because if I go, the molar mass. If I go into the lab and I have to measure the mass of copper 2 sulfate pentahydrate, I can't take the water out. So in order to get the copper 2 sulfate, I have to take those water particles in there. If I looked at it, it would still look like a powder. It's not going to necessarily look like it's wet, but the molar mass here is going to be different, and that's what we need to consider here. So we're looking for the mass. We're going to solve for moles first. Okay, so the moles are going to be our molarity times our liters of solution. It tells us that we need to get this many moles, 0.0438 moles of copper 2 sulfate. But our molar mass is going to be a huge molar mass, 249, because it is copper sulfate, plus 5 waters involved in there as well. And so our final answer should be 10.9 grams. Okay. So those are just 3 different of multiple different types of problems that you could do in order to solve something about solutions. We also know that we're looking at particle pictures. We spent a lot of time talking about particle pictures. And so if I wanted to look at something like aluminum nitrate here. So aluminum nitrate would be a solid in a crystal form that would have 1 aluminum atom or 1 aluminum ion for every 3 nitrate ions. Yes, the anions that are there. So aluminum are the cations, and these would each be nitrate, NO3 minus. And if we tried to put this into water, what we know is that these would spread apart completely, right? And so this problem is a little bit tricky in that it says it's added to distilled water to produce a solution of a concentration of nitrate that is 0.1 molar. Well, what's the concentration of the aluminum plus 3s in this solution? Well, we'd want to recognize that our equation, or our dissolution equation, would have aluminum nitrate dissolving into 1 aluminum for every 3 nitrates. And so a quick stoichiometry problem, or a quick conversion of 1 mole of aluminum for every 3 moles of nitrate would give us 0.033 moles of aluminum ions. This is one where it would be very easy for us to quickly look at this and say, oh, there's 3 aluminums for every 1 nitrate, so we would just triple this. Many students would get this wrong by saying that the answer is 0.3, because they didn't take the time to write this equation out, set up the problem to say, no, it's the conversion is from nitrates to aluminums, not aluminums to nitrates. And so we divide by 3, not multiply by 3. So that's a understanding what the picture would look like in your brain, and taking a look at and taking the time to write out the math on a piece of paper is going to be a really important practice for you to do. All right. Our next topic talks about 2 methods of separation, and we're going to be looking at the argument between the particles and the macros, like what we see from the outside and how that tells us about what's happening on the inside. Okay, we're going to look at 2 methods of separation where we're saying that we have a liquid solution that cannot be separated by filtration, right? So this is not a sand and water kind of a separation. This is something where I look at the solution, because it's a homogeneous mixture. The way that I separate out the 2 different parts is going to be really, it's going to be a lot more difficult, and I have to take advantage of the differences in the intermolecular attractions, right? So that's why we spent some time talking about IMFs earlier on at the end of last week, and they just keep coming back because it's a really important topic. First one is chromatography. There's a couple different forms of it. I'm going to speak today mostly about paper chromatography, but we're going to look at the difference in the strength of intermolecular forces between the particles and the surface on which they interact. And then we're going to look at distillation, which it looks at the difference in the boiling points of substances in order to separate them out. So in a chromatography setup, you would have something that looks similar to this. So let me just explain some of the different parts to what's happening in this lab here. Okay, so we have 3 different mixtures to be analyzed, and remember that the chromatography, each of these 2 solutions that or each of these 2 methods that we're looking at have to be a way of analyzing a mixture. So we have at least 2, if not multiple, different substances in there. Take a second just to look even at those 3 colors that I chose. Should be colors that stand out to you as something that are mixtures of colors, and that's how we could analyze them. So a typical thing that you may have done in class is that you looked at food dyes, and you looked at how to separate out the food dyes into each of the pigments that are found in between or inside of them. They don't jump out right at you when you just look at them, but chromatography would help you to understand that. We would put them on a piece of what we call chromatography paper, and chromatography paper would be defined as the stationary phase, because the chromatography paper is not necessarily going to move. We're going to set it up, either we tape it to the side of a beaker, we hang it over a stirring rod. There's all sorts of ways we can get it to stand up straight in a beaker like this. But what you would want to know is that we have a piece of paper that part of it is sticking in at the bottom, what we call a solvent, which is the mobile phase. There are 2 different kinds of solvents. Going back to our intermolecular forces, we could have a polar or a non-polar solvent, and we can talk about why you would use each of those. But what's going to happen is that as the mobile phase moves through the stationary phase, that's really fancy terminology for saying as the solvent moves up through this paper, right? The solvent is, if you've ever put a piece of paper towel in water, and you know that the water will move through the piece of paper or through the paper towel. Same thing happens here, right? As the solvent is moving through this paper, it's going to pick up particles from the mixture to be analyzed. And what we'll see is that the component parts of the mixture will travel at different rates. That some of that's a little bit of it's based on size, but it's mostly based on the polarity of the particles. So the larger particles would move more slowly, and the particles with a polarity which matches the solvent will move farther. So if we had a polar solvent, the components in here that are polar would stick to those polar solvent more strongly and move farther with them. If we had a non-polar solvent, the parts of the mixture that were non-polar would stick to the non-polar solvent and would travel further, right? So this is a key understanding here. The particles in our mixture that have a polarity which matches the polarity of the solvent will travel farther. Okay, so here's the setup. Let's look at how this would look over time. So we would start, this is the beginning of our experiment. And after, I just made up some arbitrary times, but let's say 30 seconds, what we're going to notice is that our solvent started to move through the paper. Okay, and as it passed this line where we initially had our mixtures, it started to separate out the 2 components of the purple, the 2 components of our orange, and the 2 components of our green. And as another 30 seconds goes by, we have more of our solvent moving through the stationary phase, and we see further separation of the component parts of our initial mixture, until we get to a point where the solvent is somewhere near the top of our chromatography paper. We would not want it to go off, and we certainly don't want the pigments or whatever our samples are to go off of the paper. And so we would probably stop the experiment. 90 seconds seems a little short, maybe. It could be something closer to 5 minutes. We would just take a note of what the time is, and we'd be watching this to make sure that our solution here doesn't go off the top of the paper. Okay. So this shows us that we absolutely had mixtures to begin with, and these mixtures had component parts that seem like they're kind of similar to one another, right? If I looked at this purple seemed like it was made up of a red and a blue, and it seems sort of to me like I could probably make an argument that because these look like they've traveled about the same distance, they seem like this red that came from the orange and the red that came from the purple seem like they're pretty common or pretty similar. But I could take it a step further by trying to do some mathematical analysis of this. Okay, so some measurements that I would make is, first of all, I would be really clear on where the origin is. And so typically you would make a mark on your chromatography paper with a pencil or with a some sort of a mark on there so that it's clear to see what is there, but it doesn't, it's not made with ink that's going to travel along with whatever your sample is. And then we're also going to measure the line up here, which we would call the solvent front. So how far did the solvent travel? And we would come up with a measurement here. And then we're going to calculate something that we would call, we could measure the distance that each of the pigments traveled here, right? And we're going to measure something we call the RF factor. Okay, and this is defined as the distance that's traveled by a sample. So here would be, we're going to calculate just for red, the distance that's traveled by red as compared to the distance traveled by the solvent. Okay, this number is always going to be less than 1. And what we would see is if we measure these 3 different things, we should probably get 3 different numbers that are each kind of a percentage or a fraction of the total distance that was traveled. Okay, so if we wanted to find what is the RF factor for the red pigments, the distance traveled by the red sample divided by the distance traveled by the solvent, right? And what we would do is we could calculate for both of these samples, and if the numbers were within an acceptable margin of error, then we'd say that that's further evidence that those dyes are the same, or that those samples are the same. We could do the same thing for yellow. We would just take the distance that was traveled by the yellow sample as compared to the distance traveled by the total distance by the solvent, and we would compare our answers here to say, are these similar? And finally, we could do the same thing for blue. Okay, so that's how chromatography works. We're going to calculate an RF. We said earlier, there's a couple of different ways to do it, but this is the most common way that students would do it in a chemistry classroom. And I've seen a couple of different versions of this asked on AP chemistry tests in the past, and they've all related to this form. So I thought that this would be a good lab technique for us to review together. The second the kind of separation technique that was suggested that we review here today is distillation. In our distillation, we're going to be looking at a mixture, but again, this mixture must have 2 different component parts that have different boiling points. And what we're going to do is we're going to be able to separate them based on the fact that they have different boiling points. And so you have a setup that looks something like this setup over here on the right-hand side of the page. You have a heat source over here. Your sample goes into this container on this side. And what we're going to do is we're going to slowly heat this mixture to a temperature that is in between the boiling points of the 2 liquids. And I'll give you an example in just a minute, so stick with me. And what will happen is the solution that will boil first, the solution that's at the smaller temperature, not the solution, I'm sorry, the liquid that is at a lower boiling point will boil first. As it rises through here, we'll read its temperature. And then this is called a condensation tube. It has cold water coming in here and then being released out here. And so you've got a continual source of cold water in here that's going to continue to cool off our gas vapor. As it cools off, it will fall down into here. So we have gas that's boiling here. It's condensing as it falls through here, and then it collects over here. And so now we've had a separation of our 2 different solutions. So let's look at a little bit more specific example in this picture. So let's say we have a mixture that has solution 1 with a boiling point, or liquid 1 with a boiling point of 75 degrees Celsius, and the second liquid has a boiling point of 150 degrees Celsius. What I would probably do is heat the solution to something like 85, maybe 90, something that is certainly above the boiling point of my first part, but below the boiling point of my second part. And what I would see as I did something at 85 degrees Celsius, I would notice that I would see some gas vapor that starts to rise, goes past our temperature, our thermometer, and we would notice the temperature on here probably staying pretty common, or pretty solid at 75 degrees Celsius, because temperature is not going to get above 75 until all of that has boiled off. And then it will start to condense in here. and that condenses again because we have some cold water coming in through here, and the cold water is then released out on this side. We would have a tube that's probably connected to a sink on this side, and then it goes down the drain on this side. So just a continual stream of cold water that keeps this cold, keeps our gas condensing over here, and it finally falls into our receiving flask over here, so that we end up ultimately with, if we did this perfectly, what did we talk about yesterday? Perfect magic chemistry land. In perfect magic chemistry land, you would have solution 1 is all in the receiving flask on the right, and solution 2 would all be in this original flask. Okay, and now we can continue to analyze them, or we could just say that we have separated our 2 different solutions using distillation here. Okay. Here's a problem that came off of a recent AP test, I believe. Student performed a distillation. In this case, instead of having just one, we go back here, instead of just having one receiving flask, what the student did is they collected up all of the solution, or all of the liquid, they would call it the distillate. Thank you, there's that vocabulary word I was missing. The distillate from temperatures from, let's say, 15 through 100. And then they switched out real quickly the flask, and they collected up a different sample. All of it was at about 100 degrees, 98 degrees Celsius. They had a third sample that was for anything that was produced while the thermometer read 100 or 98 to about 125, 128. And then lastly, all of the solution that was here. Okay, and so this would be the same setup, but 4 different flasks that collect up the data. As I collect up the solution, the distillate, over what range should the student collect the distillate of the compound with the stronger intermolecular forces? I told you we're not going to get away from these stronger intermolecular forces. So we should be able to read this and say, all right, we have clearly two different boiling points here. So this is one of the liquids has a boiling point that I would say is about 99 degrees Celsius. Okay, it looks to me like it's a little bit below 100, maybe 98, but this part right here is a is the first solution we're going to want to focus in, and then on the second one as well that has a boiling point, I would say, of about 128. And so our choice is really between those two. These are either some sort of a mixture, maybe some impurities, all sorts of different things that are happening in both of these diagonal sections. What we want to focus in on is the flat lines. So then we're just going to compare, is solution B or flask B have stronger intermolecular forces, or does flask D have stronger intermolecular forces? Think about that just for a sec. And the answer should be clear that the second solution, this one that has a higher boiling point, has stronger intermolecular forces. The reason why it has a higher boiling point, it takes more energy to break apart the molecules, or to change the molecules from liquid into gas. So that stronger intermolecular forces, would equate to a higher boiling point. All right. Lastly, we can talk about solubility, and I'm going to pick up on a little bit of this tomorrow, looking at what our time is here today. But our big learning here is that substances with similar intermolecular interactions tend to be miscible, or which is just another word for soluble, or able to mix together with one another. Okay, so if we looked at a classic experiment like this, if I was in my chemistry lab and I had access to all of these things, I would show these to you so we could mix it up, because it is kind of a fun activity to watch happen. If I put a piece of iodine, solid iodine, in water and I shake it up, we're not going to see that iodine really dissolve well in water. So you would typically just see the piece of iodine sitting at the bottom of the container. It would be in a colorless solution. We would just have water, right? So there doesn't appear to be a lot of mixture that's here. Whereas I put the same piece of iodine in a solution of C6H14, that's a liquid, and I see that the iodine mixes in, dissolves in, and makes a completely purple solution. And so the learning here is that iodine is a nonpolar molecule. and water is a polar molecule. So we would not expect a nonpolar molecule to be soluble in a polar solvent. However, when iodine is mixed with C6H14, this is another nonpolar molecule. We do expect the two nonpolar molecules to be able to interact better and to be soluble in one another. So iodine and C6H14 are both nonpolar substances, and the water is polar. So the diagram shows that the iodine dissolved in the CH4, but did not dissolve in the water. So this is a great example. Remember yesterday we talked about when you're giving an explanation for a diagram like this, we want to make sure we talk about all of the chemicals that are present. So we're not just going to talk about the solution on the right. We're going to talk about both, or all three of the chemicals that are here: iodine, C6H14, and water, to make sure that we're really kind of showing off all the chemistry that we know. Last question for today would be to look at which of these, we've got three pairs of molecules. And you probably have a picture, you have my head up here on the top over here. So I'll tell you that this molecule in the top right is a nonpolar. It's just a hydrocarbon, carbons and hydrogens. There's no oxygens left in there. So of these three pairs of molecules, if we call this A, B, and C, which would we expect to mix together? Which would we expect similar to what we saw in that last? If we put them both in a test tube together, which would we expect to mix together? And the answer is that we would expect just this middle solution, this middle mixture, to be able to mix together, because both of these are non-polar molecules, right? Here we have an OH with a hydrocarbon, so this is a polar with a non-polar, would not mix together. This is actually a non-polar as well, even though it has some chlorines, because the chlorines and the electrons are equally distributed around the molecule. This would around the central carbon. I'm sorry. This would behave much more like a non-polar molecule than like a polar molecule, and so they would not mix together. And that brings us to the end of our lesson for today. That was a lot of, like I said, a lot of lab techniques that I thought were some pretty cool ones that I wanted to share with you. So apologies for rushing through a couple of the other explanations, but seeing what chromatography and distillation look like, and the use of a eudiometer where we're collecting gas over water, I think are three important things for you to have some experience with before we end this year out. So I wanted to make sure we put some time into those. Your AP practice problems for today, for tonight to look at, and will be our warm-up for tomorrow. I will be going through the solutions to this. This is from the 2017 free response exam. I hope this looks familiar to you. And two quick questions that are there at the bottom. So I would take a screenshot. We're going to ask which of this dye is least polar, and in the unknown, how are we going to compare the unknown to one of these three over here, okay? And then I would like you to take a look at these two practice problems and see if you can solve each of those using the molarity equation, okay? Quick reminder to go back to apcentral.collegeboard.org anytime that you have any questions. Those will be that's where it's continually updated. Also remind you that we have some links at the bottom of the page for any other resources that you need, lots of other resources. And remind you or your friends, anybody who has internet access, or that has a question about internet access or is not able to use a device on a consistent basis, go to cb.org/tech, and they will be able to get some help directly from the College Board. Thanks so much for watching us today. We had a great time sharing this information with you. I hope you're doing well, and we'll see you again at this time tomorrow. Have a great day. Bye.